This lesson is on graphing the tangent and cotangent functions with, at times, changes in period, changes in phase shift, horizontal translations, vertical stretches, compressions, x-axis reflections, and vertical translations. So your tangent and your cotangent functions both have a period of pi radians, and we can see that here. So this is what's considered the first cycle of our tangent function, which goes from vertical asymptote at negative pi halves radians, where tangent is undefined, to another asymptote at the end of the first cycle at pi halves radians, where tangent is again undefined. Halfway between those two, we end up with an intercept, 0, 0. Halfway between the intercept and the leftmost asymptote, we have at negative pi fourths radians a y value of negative 1, and at pi fourths radians we have a y value of 1. So these 3 points are actually the key points that we graph, and then we have the curve that approaches the asymptotes. For cotangent, the first cycle is shown right here. And its leftmost asymptote is at 0 radians, where cotangent is undefined. Its rightmost is at pi, where cotangent is again undefined. Halfway between them, there will be an intercept at pi halves, 0, and then at pi fourths, our cotangent is positive 1, and at 3 pi fourths, our cotangent is negative 1. So we graph those 3 points, show it approaching our asymptotes, and then we can see it extended with other cycles to the left and the right. One thing to keep in mind is that there's no amplitude for either function, since they don't have maximums or minimums, and amplitude is defined as half the distance between the maximum and minimum. They also don't have any midlines, since a midline is defined as the horizontal line that goes through the middle or halfway between the maximums and minimums. But the parameters of A and K can still create transformations that can translate our tangent and cotangent functions up or down. They can give it a vertical stretch or a reflection across the x-axis, and so on and so forth. All right, here for quick reference are from our unit circle, and using our quotient identities that tangent is sine over cosine and cotangent is cosine over sine, we have the first cycle's key points, where these are our x values that we use, and these are the corresponding tangent values, the undefined being our vertical asymptotes, and then these being the y values, those 3 key points I was talking about on the previous slide. Same thing over here for cotangent. So this is a quick reference in case you need it. All right, here we see the structure of our tangent and our cotangent functions with all of our parameters. One of the things to keep in mind is that to calculate the period, we have to take pi, which is the period of tangent, y equals tangent x and y equals cotangent x, the parent functions, and divide by our parameter of 1 over b, its positive value, and that creates or calculates the period. Phase shift is calculated the same way for tangent and cotangent as it is for sine and cosine. And this is what I was alluding to earlier. Your parameter of A, even though we don't have an amplitude, still creates a vertical stretch, vertical compression, and or reflection across the x-axis. And your parameter of K still creates vertical translation, but has nothing to do with a midline. We could use the same trick for scales. That could be helpful. Pi fourths radians, we think that'll work. We can use that, or we can use something else. When we graph tangent and cotangent, the key thing is to figure out where the asymptotes are moving to, and then to graph those key points between them, as I was discussing earlier, and then draw in our curve. All right, let's look at graphing g of x equals tangent of x divided by 3. So this would give us g of x equals, we'd have a 1 times tangent, and x divided by 3 would be our 1/3 x, and structurally speaking there's a minus 0 there. And so the 1 is our a parameter, the 1/3 is our 1 over b. The opposite of that minus 0 is technically our c, And then also we could put in a plus 0 here to show that our k value would be 0. So in this case, we basically have a period change is what this is going to take. So when we calculate our period, we're going to take pi, because we're graphing tangent, divide it by our 1 over b, which is positive 1/3, and that would be pi times the reciprocal of 1/3, which is 3, and that gives us a period of 3 pi. Now, in transformation terms, this 3 right here is b, and that is telling us, since b is greater than 1, that we have a horizontal stretch by the factor of 3. Our phase shift, we're technically taking the opposite of the 0, which is still 0, dividing by 1/3, anything divided by, or 0 divided by anything is equal to 0. So that means we have a phase shift of 0 radians, which means we have no translation in this problem from left to the left or to the right. All right, so now graphing. So our axes here, we're going to look at graphing 2 cycles of our function. So I'm going to graph the first cycle, wherever it ends up, and then graph another cycle, which I can graph either to the right or to the left. It would not matter. So I'm going to put my x-axis in the middle because I don't have to worry here about any sort of translations up or down that's going to affect that, or vertical stretches that are going to affect that. And tangent. So now I'm graphing tangent. So it's helpful to remember that the asymptotes of the first cycle of tangent occur at negative pi halves and positive pi halves. What's going to happen with them is that they are going to be stretched vertically by a factor of 3. So this horizontal distance, or sorry, I said vertically, I meant horizontally. They're going to be stretched horizontally. This horizontal distance is going to triple to the left of the y-axis. And it's also like taking this negative pi halves times 3, which would be negative 3 pi halves. So this is actually going to be where our first asymptote is. And then your pi halves, this horizontal distance is tripling, or 1/2 pi is being multiplied by 3, which gives you 3 pi halves. This is where our asymptote is going to end for the first cycle. So when I go to graph this, what I'm looking at is I need some space over here to get to that negative 3 pi halves. And my scale, possible scale, I'm looking, I can take the period of 3 pi and divide it by 4 and use 3 pi fourths, or I could use a factor of that, such as pi fourths. So I like pi fourths, and we actually do have enough squares to use it. We need to get to 6 pi to do two cycles, and that would require 24 squares. Here we actually, I think, have 26. So we have enough space to do that. So I need to get to that negative 1/2 pi, which is going to be 6 squares. So I need at least 6. I'm going to add a 7th over here. And so my scale is a pi fourth scale. So every 4 squares is a multiple of pi. So this would be pi, 1, 2, 3, 4, 2 pi, 1, 2, 3, 4, 3 pi, 2, 3, 4 pi. And backing it up, this would be negative pi. And this would actually be negative 1.5 pi. I'm going to put that there because it's an asymptote. And this would be 4.5 pi. All right. So it is required that you graph the asymptotes for tangent, and asymptotes are always graphed as dashed lines. For my y-axis, I'm just going to use a scale of 1 unit. You could use also a scale of 1/2 unit here if you preferred. So, like I said, here's our pi halves. This asymptote is 2 squares right here. So it's getting tripled in distance. That'll be 6 squares. That's 2, 4, 6. And that's the negative 1.5 pi that we get by multiplying negative 1/2 pi times 3. The other asymptote is pi halves, which is here. It's the rightmost end for that. And it's going to triple in distance to the right of the y-axis. So 6 squares there, 2, 4, 6, and ends up here at 1.5 pi. Now I have to graph 2 cycles, which means that I'm going to need, this would be the first asymptote in the next cycle. I need the second asymptote, the ending asymptote in the second cycle. So I've got 2, 4, 6, and another 6. I've got 12 squares. So there should be 12 squares to the next asymptote. 2, 4, 6, 8, 10, 12. So that asymptote is going to be right here at 4.5 pi. All right, now tangent. Halfway between its 2 asymptotes, it has an intercept. So halfway between these two, we would have 0, 0. Halfway between these two, it should be 6 squares, would be at 3 pi. There would be an intercept. So 3 pi comma 0. Halfway between this intercept and each of the asymptotes, we have another point. Now with tangent, we have to realize, and you can see this going back to this, that you have the negative one first, moving left to right, and the positive one second, moving left to right. And that's not going to change unless we have an x-axis reflection. So when we graph this, we are looking at halfway, which would be 3 squares. We would have a y value of -1. Halfway, which would be 3 squares, we have a y value of +1. Same thing here. So these 3 squares, we'd have -1. 3 squares over, we'd have a +1. The tangent function, so this end is going to -infinity, so it's concave down here. And then this side is going to go to, the right side is going to go to +infinity, so it's concave up. So you have to draw that concavity there. So we have this concave down side going towards the asymptote, and then concave up going towards the asymptote there. Same thing here, concave down on the left this time, concave up on the right, and going towards its vertical asymptotes. And now we graph 2 cycles of this function. All right, let's look at this one. So here we have y equals cotangent of 2x. So key parameter here is our 2. That's our 1 over b parameter. And so the period here would be pi divided by 2. No need to simplify that. So we have a pi halves radians, period, which means that everything has to happen in pi halves radians. Phase shift. So we can see here that nothing's added or subtracted from the 2x quantity, so we'd have 0 divided by 2, which is 0 radians for a phase shift. All right, and again, we need to graph 2 cycles. So to figure out a possible scale, I would take that period and divide by 4. So my pi halves divided by 4 would be pi halves times 1/4, which would be pi eighths. So I'm going to use a scale of pi eighths. So now cotangent, which is what I'm graphing, the first asymptote for cotangent is the y-axis, x equals 0 radians. And so it's not going to move from there unless we have a phase shift. That's the nice thing about graphing cotangent. So if you want to graph all positives, then you can push your y-axis over here. You don't have to worry this time about any negative values for your angles. All right, and so that pi eighths, so that means every 8 squares is pi. Halfway between 4 squares would be pi halves. Halfway between that would be our fourths. So this is 1 pi fourth, and this is 3 pi fourths. And for y again, you can use a scale of 1, you can use a scale of a half. Those are pretty much your choices there. All right, and then asymptotes would be here, because it's not going to move because there's no phase shift. And then pi halves radians, so we have another asymptote there, which is 4 squares, another here to end the second cycle. Halfway between those, we'd have intercepts here and there. And then cotangent, remember, has to start with 1 on the left, -1 on the right. So it's reversed or flipped from tangent. So halfway would be a +1. Halfway would be a -1, +1, -1, and then draw in matching the asymptotes with the correct